Alright, so let's recite umul kitab before we proceed. This is what you have learned in week number 1, which is introduction to mass transfer. So I believe that now you can explain the definition of mass transfer. So remember the keyword, we are talking about matter or component move from one place to another place. Okay, the reason why it moved from one place to another place is because of the difference in concentration. Okay, so you define again what is difference in concentration. Difference in concentration means that it has moved from high concentration to lower concentration, or you can say due to the concentration gradient. Okay, so when you have this situation, all right, when you have this definition, it shows that you understand the movement, okay, the movement of particles. It can works on for fluid, for let's say, so it can be applied to gas, it can apply to liquid, okay. So it also can be done for solid actually, okay. But the rate of mass transfer for solid is much slower compared to the rate of transfer for the gas, okay. So I guess that you have learned this in your SPM level already, okay. All right. So when you want to explain, all right, you have to make sure that you keep focus on one component, okay, one component, right, when you try to explain, okay. So this can be referred to the next part, which is to look at one particular molecules or one particular matter, okay, one particular component, okay. So this diagram, okay, if you look at this diagram, it doesn't mean that you have to assume everything in liquid form. It doesn't mean that you have to assume everything in gas form, okay. So just focus one by one. If you're given the situation in gas, so you are explaining the motion in gas or the transfer in gas, okay. All right, so when you would like to explain, if you're given one component, that is easy. You just mention about the yellow component or orange component here, okay. So the component that you're talking about, you refer to how you want to define the movement of that particular component from one place to another place, okay. And then you can explain why it happened, okay, why it happened, and then in what direction, okay. So remember to mention about that, okay. So it's about transferring or movement from one place to another place. So what is moving? So you're talking about the particles, the dye particles, or the yellow component, okay. The yellow component move from one place, means that from left to right, okay, from left to right. Okay, why does it happen? It happened due to the concentration difference. What are the concentration difference represent from? It represents from the difference of concentration of yellow component here or dye molecules here, okay? Because the concentration of water remain the same, okay? If you look at this, they are constant, okay? They are remain constant, all right? So that's why you said that only molecules of dye transfer, okay? From left to right, from left you have high concentration, left you have lower concentration of dye, therefore dyes, the molecules of dyes move from left to right, okay? The reason due to the difference in concentration, okay? So that is how you measure, okay? So if you were to explain about more than one molecules or one or more component, more than one component. Okay, so you also have to explain something like that. Okay, in the situation, okay, the concentration of water or the surrounding remain the same, except the concentration of molecules of yellow dye and the concentration of purple dye. Okay, so when you have this, okay, so don't explain in one word for both components. So explain one by one. Okay, so go for the yellow until you finish explain about the yellow, then you explain about the purple. Okay, until you explain everything. All right, so that is when you're talking about more than one components or more than one molecules or matter. Okay, all right, so let's proceed. Today we have more serious things that we need to discuss. So this is just for the revision. Okay, Fick's law for molecular diffusion. So I guess that some of you still confused regarding to the Fick's law. Okay, so some of you might still confused on the Fick's law. All right, so Fick's law is the basic theory when you talk about molecular diffusion. Okay, it is derived from the original equation. So the original equation is in the mole fraction form. So this is your original equation. Okay, they are based on mole fraction of the component. So if you're talking about liquid, so this is the mole fraction of the liquid. Okay, if you talk about gas, this is the mole fraction of the gas. Okay, the mole fraction of the liquid or the gas. Okay, so what can we do about the mole fraction? Okay. So the mole fraction terms here can be transformed into concentration terms. Okay, in terms of concentration. So what concentration are you talking about? So this is the concentration of the gas. This is the concentration of the liquid. It doesn't matter because we are dealing with molecular diffusion. It's a molecules. Okay, so you have molecules in liquid. You have molecules in gas. Okay, so you are given two terms, two basic terms here, which is mole fraction or concentration. In terms of mole fraction, which is X, in terms of concentration, which is C. Okay, so it doesn't matter whether you're given liquid or gas. So this is the basic formula, basic theory. Okay, it is applied for diffusion, whether it is liquid or whether it is gas. It doesn't matter. Okay, all right. But if you were to calculate, meaning that you would like to know the magnitude, okay, the strength of the diffusion, okay, so you need to look the difference, okay, of the number, okay, because you know that 5 is greater than 2. Let's say, and you are given two numbers, number 2 and number 5, but 5 is greater than 2. So if you talk about the strength of something, you look for the number. Okay, you look for the number. All right. So you're going to say 5 is stronger if you're talking about diffusion, if you talk about flux. Okay. So what is flux actually? Okay. So let me explain a little bit regarding to flux. Okay. So I believe that you have learned about magnetic or magnet. You have learned about electricity, okay, in your physics subject, all right, in your physics subjects during XPM level, okay, all right. So when you talk about electric, you can calculate the current, Okay, you can calculate the current. All right. And then if you remember, electricity also consists of electric field. Okay, medan electric. Okay, so you can say that the electric field is stronger or weaker, right, during that time, SPM level. Okay, all right. So physically, you can feel that. You can, when you feel the electric field, so that is electric flux. Okay, so you can describe it is strong or it is weak. But how strong that you can define it is strong. Okay. Now is the time for you to know how to calculate to get the values to represent easily for ordinary people, so that people can understand much better. So you might want to know, is it 100? Is it 1000? Is strong? Okay, so you have to define. Okay, how do you define? By showing the calculation. Okay, so you have electric flux. You can also have magnetic flux. From magnetic field, you get magnetic flux. From electric field, you get electric flux. So from diffusion, you have molar flux for diffusion. Okay, so that is how you look at flux. Why do you call it flux? Molar flux, you are talking about concentration here, the strength of the concentration. Because you say that before, the definition of mass transfer, they are related to the concentration gradient. Okay, so bila concentration gradient, so it reflects to the mole or molar. Okay, all right. So when you want to calculate the strength, it is molar flux. Okay, all right. So that is how you look at these two terms. Okay, two terms, mole fraction terms and concentration terms. Okay, and you are given also the length, okay, the distance of the flux, because you're talking about moving from position 1 to position 2. Okay, so position 1 to position 2, how long is the distance? Okay, all right, how long is the distance? So you have to know the distance, because in the formula, in the Fick's law, you have difference in distance. Okay, difference in distance represent final distance minus initial distance. Okay, final distance minus initial distance. So if you say that the initial distance represent 0 meter and the final distance, okay, final distance is, let's say, 3 meter. So therefore, difference in distance is 3 minus 0. Okay, 3 minus 0. We always have upper limits minus lower limits. Okay, but before you can represent which one is positive direction, because dz represent also the direction. So if you say that from left to right represent positive direction, therefore from right to left represent negative direction. Okay, so this is what you have to look for to understand much better. Okay, so luckily what we're going to do here, just a linear direction. Okay, linear direction. Linear means straight line direction. We are not talking about circular direction. Okay, just linear direction. And when you do your calculation, it also represent linear direction. And the linear direction that we are going to use for diffusion is only horizontal direction or vertical direction. Okay, that's all. All right, a very simple law. Okay, so don't just say that Okay, when you proceed to the next theory, don't just simply say that if the question doesn't give you in terms of what you want, it doesn't mean that you cannot do the calculation. Okay, because it is derived. Okay, it is derived from the original fixed law. Okay, it is derived from original fixed law. Okay, and I did mention that when you derive the equation, you start from the mole fraction terms, then you get in terms of concentration terms, and then you get in terms of partial pressure terms. Okay. Basically, okay, when you're dealing with liquid, normally you're given in terms of concentration. When you're dealing with gas, okay, when you're dealing with gas, it is in terms of partial pressure. Okay, but can you calculate in terms of concentration for gas? Yeah, you can use that. All right. But when you use that, all right, when you use that, the value that you use for concentration is very small. Okay, it's very small, right? Because when you talk about concentration of gas, okay, concentration of gas, they always represent a small value of concentration. Okay, all right. So what you can do is to play around, okay. If you want to use in terms of partial pressure, look at this equation. Okay, because you derive the partial pressure terms from the concentration terms. Basically, they are the same because the roots are the same. The roots where they begin are the same. Okay, if you're given the information, the information that are given to you is in partial pressure. So use this formula directly. Okay. If you're given in terms of concentration, okay, you can use this one also, no problem. Okay. But if you want to use in partial pressure, these terms, how you manipulate this term to be this term is using this formula of conversion that you're going to represent, which is the partial pressure divided by the what? Gas constant, all right, and divide by temperature. Okay, so they are derived from the same equation. So don't confuse this. Okay, don't confuse. Right? Okay, and then I ask you to use this equation. Okay, because this example is very straightforward, because you know that you're dealing with gas and you're given information in terms of partial pressure. So it's easy for you to calculate. All right. So understand why you need to do the calculation based on partial pressure or based on the concentration. Okay. Okay. And then this one again. All right. Okay. If you want to describe, okay, different in concentration or concentration gradient. So normally you're going to say that concentration at position 1 for component A, okay, is lower, is higher compared to the concentration of component A at location or at position 2. Okay, so because they are derived from the original fixed law, okay, you can also represent the concept of concentration gradient in terms of partial pressure. Okay, in terms of partial pressure. Okay, so you can play around with this information. Okay, where the partial pressure at location 1 for component A is greater than the partial pressure at location 2 for component A. Okay, so this is how you describe. Again, because I did mention this before, you mention about A here, you mention about A here. If you want to mention about B, you have to mention about B. So B to B, the only difference you're talking about is location 1 and location number 2. Okay, all right. So that's one. Explaining about JA or molar flux of diffusion for component A, you get the value. Okay, and then if you want to calculate based on the same direction, based on the same diagram, molar flux for component B, okay, molar flux for component B is equal to JBZ. Okay, JBZ. The magnitude that you get are the same. Why? Because we are talking about equimolar. Okay, equimolar. But the motion, the movement are in the different direction. Okay. For A, you say that left to right is positive. So that's why you have positive here. Okay. So based on the same diagram, from right to left, it represents negative. So that's why you have negative value here. Okay. Just to represent the net diffusion of A is in the positive direction, and the net diffusion of B is in the negative direction. But the magnitude that you get will always be the same. So, do you have to calculate JB if you have calculated JA? Can you answer the question now? Do you need to calculate JB after you calculate JA?
No, Miss Ita.
No, no need. Don't waste your time. Because you are given the condition of equimolar. Okay? You have to understand that. Okay? Don't waste your time. If you've shown one calculation, and then you show the relationship here, okay? And then the next thing you need to do is just put the value. Okay? Just put the value. That's why we can have another equation. So altogether, you have JAZ. You can also have JBZ. So you can also have a relationship of JAZ, which is equal to negative JBZ. Okay. All right. Okay. Now you are looking for this diffusion of a gas also. Okay. Example 6 to 1. And you're also given the partial pressure. Okay. All right. So let me remind you, you are given the gas constant here. There are many values of gas constant with different units. Okay. So what is given here is meter cube atm over kilogram mole Kelvin. Okay. There are many values of R that you can have in this world. Okay. With different units. So which one that you have to use? You have to refer to what you have in the questions. Okay. Okay. First step, you might want to use, you want to refer to one of these, or let's say, okay, one of these. Okay. But, okay, if you're given in terms of, let's say, Pascal, okay, in terms of Pascal, let's say. So this is Pascal, right? This is ATM. Okay. So you have to know whether Pascal is the same as ATM. Is 1 Pascal equal to 1 ATM? If they are the same, then you can use this formula. Meaning that 1 to 1. 1 Pascal is equal to 1 ATM. Then you can use this formula. But if 1 Pascal is not equal to 1 ATM, then you need to do the conversion. There are two types of conversion that you can use. Okay, whether you change this Pascal to ATM or you change this ATM to Pascal. Okay, so you cannot use the constant given directly without looking at the units. So make sure the units are consistent. All right. And then here you have meter cube. Therefore, the unit for length is meter. If you're given centimeter, then convert to meter. Okay. Here you have 1 meter. Okay. Sorry. Here you have 1 meter, 0.1 meter, and this 1 meter. Then just use directly. Okay. So make sure that you know how to do conversion. Okay. Any question before I proceed to diffusion together with convection? Any question, you just switch on your mic and ask question because I cannot see your face when I'm giving you the lecture. So diffusion process together with convection, right? So everyone can read this. I don't have to read for you. So it's come from Fick's law also, okay? But Fick's law equation is based on diffusion in stationary fluid, okay? Stationary fluid, okay? There is no net movement or convective flow, okay, of the entire phase of binary mixture A and B. Okay, so when you are given diffusion with convection, okay, just look at the arrow down here. Okay, arrow where? Okay, so when you look at these two arrows, one is VA, one is VAD, one is VM. Okay, what is VA? Okay, look for the definition of VA. V represent velocity. Okay, actual velocity of component A. Okay, when you have A here, it represents component A. Okay, actual velocity of component A relative to the stationary point. Okay, actual velocity of A relative to stationary point. For let's say, okay, just give some ideas lah. Okay, what does it mean by that? Okay, all right. Okay, so let's say you are driving a car. Okay, you're driving a car, right? So the component that you're talking about is the car. And then you have a speed trap along the side, along the road. Okay, all right. You have a police. Okay, they are tracking on your speed. Okay, but they are the policeman sitting at one place without any motion, without movement. Meaning that the police is at stationary. What is moving? Your car is moving. Okay, your car is moving. So when they take the speed of your car, okay, it represents VA, the actual velocity of the car relative to the stationary point where the camera is placed. Okay, so that is represent actual velocity relative to stationary point. Okay, so definitely lah, dia kata kereta you laju kan. Okay, because dia duduk, dia diam, your car is moving very fast. Okay, so the velocity that they take for your car represent the actual velocity. Then you go for the VM. Let's look at VM. VM is the velocity of the buck relative to the stationary point. Okay, velocity of the buck relative to the stationary point. If you look at VAD, diffusion velocity of A relative to the moving fluid. Okay, fluid. Okay, now when you talk about buck, meaning that you are talking about the whole thing. Okay? Okay, if you talk about A is only one component. One. All right. So when you talk about bulk, you have A. A bulk of A. A bulk of A. Right. Right. And then it is relative diffusion. So we are talking about diffusion velocity. We are talking about velocity of the bulk. We are talking about actual velocity. Okay. So you can say that VA, which is actual velocity, is the summation of diffusion velocity plus velocity of the bulk. Okay, so you can say that VA is the resultant. Okay, VAD plus VM. Why we have this? Because we are talking about diffusion and they have direction. Okay, so when you go back to diffusion of flux, definitely it is occurred due to the concentration gradient. So now you can say that JA, which is molar flux, is equal to VAD, which is diffusion velocity of A, multiplied with the concentration of A. All right. So this is when you talk about diffusion flux. Okay. So in the diffusion process together with the convection, so you have to add both of them based on what you have for the velocity. So VA is equal to VAD plus VM. So if you multiply each component or each vector that you have here with a scalar, concentration is scalar, velocity is a vector. Okay, so you multiply each item. So this is what you get. Okay, this is what you get. All right. So when you have this part, okay, CAVAD is JA. So you can represent JA here. Okay. And CAVM is the convective flux. Okay, convective flux. All right. And then CAVA, this is the total flux. So senang cerita, when you're given diffusion together with convection, the formula that you need to use is NA is equal to JA plus CAVM. Okay. All right. So the total flux of A is given by diffusion flux of A plus convective flux of A. Right. So this is the moment that you are talking about when you are dealing with diffusion plus convection. Okay. Now, so let's look at the next part. Remember just now? Okay. You need to know this formula and what does it represent? Diffusion. And the next one is convection. Okay. Both happen at the same time. Okay. So you play around with the formula. Okay. So JA can also represent by in terms of mole fraction, in terms of concentration, and so on. Okay. So you can represent JA by negative CDAB that you have from the Fick's law. Okay, you can have from the Fick's law. All right. So the convective parts, okay, the convective parts, which is CAVM, okay, CAVM, all right. So you can substitute from these particular terms. CAVM is equal to the total flux of A plus total flux of B. Okay, total flux of A plus total flux of B. All right. So you can have component A and component B. Kalau you ada satu di komponen, tak perlulah ada NB will always represent 0. Okay. So when you have this formula, okay, when you have this formula, you can just go back here. Okay. All right. So remember, we are talking about mixture of A and B just now. Okay, mixture of A and B. Right. Fick's law, ingat balik, it is only referring to the stationary flux, but when you talk about diffusion with convection, you are dealing with net movement or convective flow of the entire phase of binary A and B. So you talk about both of them at the same time. Okay. The difference dia kena faham. Maksudnya apa? Tadi kalau Fick's law saja, you are referring to only one. A, you get JA. B, you get JB. Now, when you talk about together with convection, you can have total, which is A and B. Dia macam tu. Okay, so that's why you have total flux. Okay, total flux can be represented by the flux of A plus flux of B. Okay, so you can just substitute the value in this term, in the second term, then you get this term. Okay, all right. So this is the formula. But by looking at the formula, you still have dx over dz. You cannot do the calculation yet because you have to do something on the derivative before you can do the calculation. Meaning that you need to do the integration. Okay, you need to do integration. Okay, so that's why when diffusion combined with convection, you have this formula. Okay, if you have only diffusion, then you have Fick's law only, basic Fick's law. All right, for one component. If you want to have diffusion and convection, you have total flux. Okay, for binary mixture that you have, Na and Np. Okay, so you need to differentiate, okay, between single component and binary component. Okay, kena faham itu. Right. Next, this is the third part. Okay, first part is equimolar countercurrent diffusion. The second one is the diffusion plus convection. Now you have the third one, which is diffusion through stagnant and diffusing B. Dia macam tu. Okay, so ada yang dah buat air dah makan nasi lemak? Memang salah tak puasa kan? Okay, so I'm going to proceed. So diffusion through stagnant, non-diffusing B. So you have A and B. Remember, you have binary components, A and B. Okay. When you talk about only Fick's law, basic Fick's law, you talk about one component or a stationary component. Okay. So when you talk about convection, diffusion plus convection. Okay. So you talk about binary components, right? And then here you have diffusion through stagnant, non-diffusing B. So you are talking about binary components. Okay. So when you talk about diffusion through stagnant, so what diffuse? You definitely say that A diffuse through stagnant and B non-diffuse. Senang macam tu. Alright. A diffuse, B non-diffuse. Okay. Right. And then we are talking about diffusion of A through stagnant, non-diffusing B at steady state. So majority is about the steady state. Why steady state? Because it is easy for you to calculate. If you talk about unsteady state, it is a complex calculation. Okay. So one boundary at the end of diffusion path is impermeable, okay, to component B, right? Meaning that B cannot diffuse into section where you have A inside. Sedang cerita macam itulah, impermeable. Okay, so when you talk about diffusion through stagnant, Alright, diffusion through stagnant. So you have a stagnant component inside here. Alright. Okay. So normally you can say this based on the small tube, a very small tube. We are not talking about a pipe. Okay. So we are talking about tube. Alright, tube, eh? Okay. So you want A to diffuse. Okay, you want A to diffuse, but you have to make sure that B non-diffuse. Macam tu. Okay. Alright. So macam mana ya kalau saya nak bagi example. Okay. For let's say, kalau you pernah let's say lah, you pernah masuk hospital ke, pernah pergi hospital ke kan, and you can see that the patient tu, pesakit tu, dimasukkan air ke dalam badan dia. Contoh lah, saya bagi contoh lah. Nak bagi you faham dulu. Okay. So, dia akan cucuk jarum kan. Dan dia ada botol dekat tempat yang lebih tinggi because they want the water to flow, okay, due to the gravity and then diffuse in the body. So, normally air yang masuk tu is the mineral water kan sometimes. Mineral water pula. Yalah mineral lah. Air garam kita panggil kan kadang-kadang. Okay. So dia cucuk you punya tangan dengan jarum tu. Dan air tu pun masuklah, senyap-senyap masuk kan. Okay. So nak tunjuk bahawa concentration of, let's say you have mineral, concentration of the minerals in the water is higher compared to your minerals in your body. So that's why air itu akan masuk due to the concentration gradient. And you boleh imagine lah, okay. When you learn more, you can understand the world better. Dia macam tu. So every time you see something, try you use your brain, try to figure out why, and always put why questions. Why questions? Why? How? And how? How does it happen? Okay. And that can make your brain trigger of something. So your brain can trigger the information when you have the knowledge. When you have the knowledge. If you don't have the knowledge, your brain cannot trigger the information. No, tak nak fikir pun sebab tak ada apa-apa pun nak fikir kan. Okay. So the water with the minerals inside, okay, so you're talking about minerals lah, will diffuse into the body. Okay, the patient body due to the concentration difference. Okay, and then at the same time you have to figure out kenapa your blood tak masuk dalam tube tu, tak masuk dalam jarum tu, dan masuk dalam air tu pula. Okay, so you can nampak, you can see over there that the blood, okay, because you masukkan air sebenarnya dalam blood kan. Alright. Okay, air yang dimasukkan tu sebenarnya masuk dekat blood kan. Okay. So saya tak tahulah sebab saya tak ambil medik. Maybe you pernah ambil medik ke dulu, you lebih faham lagi lah. Okay. So saya figure out maybe air masuk tu dia akan melalui blood stream. Tapi blood tak masuk. Tak masuk semula. So dia tak ada counter diffusion kat situ. There's no counter diffusion occur between the minerals and the red blood. For let's say red blood. Okay. So what you can see based on that, okay, you are talking about the minerals diffuse through stagnant but non-diffuse blood, red blood. Senang cerita lah. Macam itulah lebih kurang. Hope you understand. Okay, so this is a tube, a very small tube. Alright, this example represents a small tube where you have a benzene liquid component in here. Benzene liquid component in here. Okay. So because it is a small tube that consists of benzene liquid here, okay. So we are talking about only one component. Ingat ya. So when you talk about diffusion, you talk about two things. Ada dua benda. Satu is about a single component. Next, you talk about two components or binary components. So you have A components, you have B components. If you have A and B, you're going to say it is a binary components. And then we also say that in the components, you have a bulk of components inside. Bulk. Banyak. Quantity yang besar. Alright. So we can say that this is a bulk of liquid benzene, a bulk of component A. But when you talk about A diffuse, there's only one component of A diffuse. So you just say that we are talking only about one A. Okay. So in a tube, okay, if component A move from position 1 to position 2, the distance traveled is equal to Z2 minus Z1. Okay, Z2 minus Z1. If Z1 represents 0 meter, Z2 is equal to 2 meter. Therefore, you have difference in Z, or the distance traveled for the diffusion, is 2 minus 0. Okay, so that's why you need to label. Okay, important, and this diagram is very important for you to understand. So you need to draw a tube. Okay, because you have liquid, it must be a tube, a container. Okay, a tube. All right. So the upper level or the surface level of the tube is considered as level Z1. You can label that. So this is Z1. Okay, this is Z1. And then the top of the tube is labeled as position 2 or point 2, which is Z2. Okay, Z2. Right. So since A would like to diffuse, so the distance traveled is Z2 minus Z1. So A diffuse, okay, where diffuse outside of this tube, okay. But outside you have component B. B non-diffuse, so B cannot diffuse. B don't want to diffuse into this tube. Okay, so what happened? Okay, so you have point number 1. Okay, maybe you have partial pressure 1. Point number 2, you have partial pressure number 2 for component A. Ingat because you cerita tentang A, you cakap tentang A. Diffusion molar of A is relevant to the partial pressure of A at position 2, partial pressure of A at position 1. Okay, so in this case, benzene would like to evaporate into air. So diffusion of benzene into air. So you have air outside. Okay, since B cannot diffuse, so you say that non-diffusing B. But in this case, okay, you can assume that partial pressure at position 2 for A is equal to 0. Why? Because you are talking about bulk of B component flow on the top of the tube. Okay, on the top of the tube. And the movement, they move very fast. High velocity lah senang cerita. Okay, so bila they move very fast, then you can say that partial pressure at location number 2 for A is equal to 0. You can assume the value is equal to 0. Okay, so because only flux occur, only diffusion occur for component A, so you have a value for NA, but since B non-diffuse, so you have NB is equal to 0. Dia macam tu. Okay, so now looks at what we can do. So these are the formula for convection just now. Now because it's involved diffusing A, non-diffusing B, therefore NB equal to 0. Okay, NB is equal to 0. Right. So since you have in terms of mole fraction, and you can also have concentration here, so you can play around with this formula, substitute into above equation. So when you substitute into above equation, you get equation number 9 in terms of partial pressure. Okay, in terms of partial pressure. But this partial pressure, you still cannot do the calculation, okay, because you still have a derivative of partial pressure. Okay, derivative of partial pressure. So you need to integrate it. Okay? You need to integrate this partial pressure. Okay, to simplify the integration, the answer for the integration of equation number 1, you can get equation number 10. Okay, so if you learn about integration, you know that when you integrate dp over dz, all right, so I think your PA is here. Okay, so when you want to integrate, these are the terms that you get. So you can refer to your calculus book. Okay, how do you integrate these terms? Okay, so that you get these terms. Okay, so just refer, because you have the formula to get these equations sebenarnya. Okay, from the integration. All right, so now if it involves diffusion of A, non-diffusion of B, so you're going to use this equation, okay, to calculate the total flux. So the total flux of A is given by diffusivity, AB, multiplied by total pressure, okay, and then you have ln P minus PA2, P minus PA1, okay, and then you need to know what is P. P is total pressure. Remember, the total pressure is involved A and B component. Okay, A and B component. So if you know the total pressure, you want to calculate the total pressure at location 1. Therefore, you talk about partial pressure of A at location 1 and partial pressure of B at location 1 also. Okay, so based on that, okay, you can have another equation which involves PBM. Okay, what is PBM? PBM is given by two equations. Okay, one is in terms of component B. Okay, another one is in terms of component A. Okay, so you can use any of these as long as you have the information to do the substitution for PBM. If you have information on B, you use this formula. If you have information on A, you can use this formula to represent your PB. Okay, so for the case of diffusion of A diffuse, non-diffuse B. So you have to follow this particular equation where you need to put that non-diffuse B represent NB equal to 0. Okay, all right, so that's all. Okay, you can try example 6.2. Okay, all right, you have to make sure that you know what you're going to do. Okay, in this subject, you get marks based on your calculation. The final answer is only a small portion. Okay, to represent you understand or not understand of the particular question or theory, you can look for your approach. But if you get, sometimes you get, let's say 1.60, and then you ask me why your answer is different than mine. Because you are the one who do the calculation, not me. That's my answer. You are the one who do the calculation and not me. Okay, so everything are there. Okay, so do your own calculation. Be confident of yourself. Okay, you can compare your answer with your friends. Okay, don't tell me that only one of you work alone. Don't tell me you work alone. There are 90 of you. Okay, you can compare your answer. If 90 of you in the class, you can compare your answer with 89 of your friends. Okay, make some effort. Okay, mesti ada effort lah nak belajar. Okay, so please do 6.2.-2. Okay, I'm going to proceed to the molecular diffusion in liquid. So this will be explained further. The theory will be used further in chapter number 4, chapter number 3, okay, that you're going to learn. Alright. Okay. So liquid extraction, example of diffusion of solutes in liquid. You can also have gas absorption. Alright. So these are the basic concepts I've explained to you already. Diffusion in liquid. Okay. When we talk about diffusion. Alright. Okay. Flux in liquid is lower than flux in gas. Remember, I mentioned to you what is flux. Flux is the magnitude that you can calculate to explain the strength of diffusion. Okay, you can calculate flux. Okay, you can calculate the flux. All right. So definitely, gas has higher flux compared to liquid because diffusion in gas is much faster. Okay, the speed is greater compared to the speed of diffusion in liquid. Okay, all right. So diffusion in liquid often quite dependent on concentration. Okay, so that's why I suggest you, if you were to have liquid, you use the calculation in terms of the formula that you use must be in terms of concentration. Okay, but if you're dealing with gas, better to use calculation in terms of partial pressure. Okay, all right. Okay, so this is a diffusion of solvent diffusion. Okay, in liquid extraction. Okay, so what I'm going to tell you is that you're dealing with solvent which is light phase. Okay, this one will explain further in the chapter of liquid extraction, but this is to explain you a little bit regarding to what you have to understand before you learn that particular chapter, because everyone will face the same situation where you have to go to the lab to do the experiment on certain topic, okay, before you learn that topic in class. Okay, so at least you understand a little bit regarding to that. Okay, solvent, always light phase, and then you have feed solution, heavy phase with mixture of solutes. Okay, so now get to know about solvent, get to know about solutes. Okay, in the solutions, in the feed solutions, you have components which is called solutes. Okay, solutes. In the feed solution, you can have A and B. Okay, you can have A, B, C, and so on lah. Banyaklah molecules dia. Banyaklah dia punya components. Alright. One of your interest components is called solutes. Interest components. So let's say you have orange juice. Your orange juice is called feed solution. Dalam orange juice ada macam-macam component. You have a variety of components in orange juice. Okay. But among that components, your interest is only vitamin C. Kena faham tu. Your interest is only vitamin C, for let's say. So, because your vitamin C is your interest that you like to separate, you want to separate vitamin C in the feed solution. Therefore, vitamin C is called solutes. Okay, vitamin C is called solutes. Okay, so your intention is to make sure that you can separate your solutes from the feed solution. How are you going to do that? Okay, one of the method to separate your solutes from your feed solution is by using solvent. Okay, by using solvent. All right. So when you use solvent, okay, you have to select your solvent properly. Not every solvent exists in this world can be used to extract vitamin C. There are many conditions lah. Okay, so when you use proper, correct solvent, vitamin C will be separated from the feed solution and attracted to your solvent. Attracted to your solvent. All right. So all the vitamin C will move to your solvent. But the other components will remain in the feed solution. Itu je objektif kita. Okay. Alright. One, you have to understand, diffusion occur. The reason is because the solvent, the concentration of vitamin C is less in the solvent compared to in the feed solution. Okay. But if you look at other components, you can also see that the other component also has higher concentration in this position compared to that position. But the other components will not diffuse. Okay, will not diffuse. Okay, why is that for? So we are talking about only only vitamin A can diffuse, but the rest is in the impermeable layer. Dia tak boleh masuk pun. Kalau masuk pun dia sesat lah. Okay, so how to achieve the separation process? So you have to make sure that you mix the light solvent together with your feed solution. Okay, you mix them together. Okay, so to increase the contact area between your vitamin C and your solvent, you have to mix the solution properly. Okay, so by doing that, okay, you can attract, okay, your solvent can attract your vitamin C, okay, in the face, right? Then you let the liquid settle, and then you can see that now you can have vitamin C, okay, attracted to your solvent. Before this, attracted to your solvent and diffuse in the solvent. Okay, but still you can have impurity in this section. Okay, impurity, which is the green molecules. All right, but the impurities that you have is a small percentage only. Okay, so later you might want to do further separation to get a pure vitamin C, for say. Okay, so before the diffusion occur, you have a separation between, you have a separated component of feed solution and solvent. Because your solvent is a light phase, it will place on the top of the solution. Then you mix the solution to increase the contact area between your solutes and your solvent. Sekarang you akan guna perkataan macam tu pula. You're going to have a good contact between your solvent and your solute. Okay. We want to have that contact because they increase the diffusion rate. Okay. So after the contact happen, then you settle the liquid. Okay. And then you can see the separation occur where you have your solutes in your solvent. The final product on the top layer is called extract. Okay, or you can say that this is solvent-rich component. Okay, solvent-rich component. Okay, the rest of the feed solution is called raffinate. Okay, raffinates. All right. So the raffinate is only consists of little bit of your solutes, okay, which is not extracted. Okay, so the one that you have on the top, which is the light component, consists of your solutes. So that's why later maybe you can have your vitamin C here, and you can to further separate the process, where later you're going to separate your solvent from your vitamin C to get your pure vitamin C, something like that. Okay, pure solutes, right? So there are processes involved. Therefore, it's easy to look at this as before the contact happen, before the mixing happen, you have two phase. Okay, one is called solvent, one is called feed solution. When the contact occur, the final liquid that you get is called extract and raffinates. What is extract? Extract consists of majority of your solutes that has been separated from the feed solution. Okay, so if you have this kind of situation, you have blue and green, you might want to say this is a binary components. Okay, you have A, maybe you can have C, you can have A and B. Okay, if you say that C is your solvent, so you have A, B, C components in the system. Okay, so one system consists of three components, A, B, C. Okay, A, B, C. A is your solute, B is other than your solute, sometimes they call it carrier. Okay, all right, and then C is your solvent. Okay, so that is how you look at it. So that one is liquid-liquid extraction. Next is about gas-liquid, okay, or gas absorption. So I'm dealing with gas and the liquid. Just now it is in liquid form, both in liquid form. Okay. All right. So this is a very simple definition, okay, on the gas absorption. So liquid always fit on the top of the column. Gas will be fed from the bottom of the column. Okay. Liquid is fed at the top of the column. Liquid flow from top to bottom. Okay, top to bottom due to the gravity. Okay, the feed gas is fed at the bottom of the column. All right, it flows randomly in the column because gas kinetics, they move randomly. Okay, they move randomly, right? To increase the contact area between the gas and the liquid, all right, to separate the solutes, you use packing inside. Okay, this is called packing. All right, packing. All right, so this packing will increase the contact area between the gas and the liquid. So if you don't have packing, you can just imagine the gas flow like that, the liquid flow downward. So you talk about a big amount of gas, a big amount of liquid. So therefore, the contact area will reduce. But if the gas move randomly, allowed to move in different channels through the packing, and the liquid move also randomly, okay, because the liquid move downwards through the channel in the packing, so therefore they meet, the liquid and the gas meet in the small volumes. Okay, so that will increase the contact area of the liquid and the gas. Why do we need a contact area between the gas and the liquid? Okay, look at this diagram. Okay, so you have layer. When you have liquid, okay, when you have liquid and when you have gas, you can imagine you have two layers. Okay, you can imagine one layer where you have your gas, another layer where you have your liquid. Okay. Diffusion only takes place in the thin film. Okay, thin film, which is the surface between the gas and the liquid. Okay, diffusion only at the thin layer. So that's why we need to increase the contact area between the gas and the liquid. If you have bulk of liquid and bulk of gas, the efficiency of the gas absorption will not be too high. It will be small. So it is not efficient. Okay. So since it's occur in the thin film, you need to increase the contact area. Okay. So the gas will diffuse in the liquid. Okay. The gas will diffuse in the liquid. Okay. Liquid, okay, hardly diffuse in the gas, but the gas diffuse in the liquid because we need a thin film between the gas and the liquid. That is how the gas enter the liquid. So gas absorption may be the place, the application is for the company if they produce, there are many applications actually, okay? It not just represent the waste gas. It doesn't mean that you're going to treat gas, okay? It's also used for the production of food that you have, okay? Kalau production of food, lagi senang kan, okay? Like you used to drink carbonated drinks kan, okay? Actually, the amount of liquid is not in the full capacity of the container. Okay, so what you have in the carbonated drinks is they consist of gas. Okay, so when gas diffuse in the liquid, you can increase the volume. Okay, maybe you have half of the bottle consists of liquid. When you diffuse the gas into the liquid, the volume will expand, so that will fill the container. Okay, will fill the container. Okay, all right. So that is when you talk about diffusion of gas into the drinking water lah. Okay, all right. So there are many things that you can do. Okay, but what happened? The diffusion only takes place at the thin film. Itu kena faham. Okay. So what do you have? So if you are dealing with gas absorption, okay, initially at the beginning you have liquid in and the gas inlet and liquid inlet. So you have liquid feed and you have gas feed. All right. And then you also have the gas outlet or the gas outlet and the liquid outlet. Okay, so when you want to label, this is called feed gas. Okay, feed gas inlet or feed gas stream. Liquid in is called solvent stream. Okay, solvent stream. The gas out is called raffinate stream. And the liquid out is called extract stream. Okay, extract in liquid form, raffinate in gas form. So you're going to look at this unit operation in the lab later. Okay, so you need to find out the location of the feed stream and the location of the outlet stream. Okay, so you're going to have a quite big equipment over there. Okay. Alright, so ni adalah repeating, but we are talking about liquid diffusion, equimolar counter diffusion, and liquid diffusion. Okay. Okay. So these are the equation that you have to deal with. Okay. That's involve what? This equation is for the pack power. Pack power. Alright. Pack power. Okay. So if you're dealing with pack power, then you have to use this equation where the equation of diffuse, the molar flux equation represented by CAV. Okay. So you can play around with this formula. Okay. And this will become this one. And you have to know how to calculate CAV based on the density and molecular weight. Okay. So you can have this in your textbook. So I want you to read from the textbook. Okay. Read and try to understand. Okay. So we are talking about, let's say, one of the example here represent a component, a solutes A, diffused through water phase. Okay, through the water phase. Okay, and then you can see that if you are dealing with the pack power, gas absorption using pack power case, so the equation that you need to use is this equation. Okay, this equation. So I want you to read first this part. Look for your textbook. Okay, so that you can understand much better. Okay, because we don't have much time. Okay, and try this particular equation. Okay, so you need to explore. There are many ways on solving this equation. Okay, so you need to explore one example. Read example that you have in the textbook and try to understand. Okay, because you have 3 applications that you have learned before. Okay, so I'm going to go through very fast. So this is a diffusion in solid. Okay, so definitely it is a slow diffusion process. Okay, it is lower rates compared to liquid and gas. Okay, but we are not focusing on this particular solid, but there are few equations that involve mass transfer coefficient. Okay, where you can deal with the transfer of molecules using the mass transfer coefficient. Okay, so you have Kc. Okay, by represent this one DAB Z2 minus Z1 to be the mass transfer coefficient. Okay, you introduce K prime C. Okay, and then if you introduce, you simplify this term. Okay, you can simplify this term using mass transfer coefficient. So that's why the symbol is only K prime C. Okay, so this is just mass transfer coefficient. Coefficient is a constant. Senang cerita. Okay, all right. And then we have mass transfer coefficient for equimolar counter diffusion. Okay, so using this formula. Okay, so you just need to know for this particular calculation. So mass transfer coefficient for equimolar counter diffusion or mass transfer coefficient topics is just for your knowledge. Okay, because you're going to learn this one furthermore in your degree level. Degree level. So I just want to mention about this so that at least you heard about this. Okay, what is mass transfer coefficient? We are talking about a constant. Simplify the equation to be a constant. Okay. All right. So you are using the symbol K prime C, Kc prime. Okay. So if you're dealing with gas, so you are dealing with a symbol of Ky prime. If you are dealing with liquid, you just present your coefficient to be Kx prime. So Y is for the gas, X is for the liquids. Okay. So you can manipulate again the equation until you get a relationship between K prime C and Ky prime. Okay, and also you can get a relationship between K prime C and Kx with the value of xbm. Okay, so what is xbm? X is the mole fraction. Okay, all right. X is the mole fraction. All right. So when you have xb, this is mole fraction of B at location 2. Mole fraction of B at location 1. Okay. So finally you have both equation for the gas and for the liquid, and then for the relationship between the Kc and the Kx together with X or mole fraction. Okay. Alright. Tolong baca dan cuba fahamkan how does it happen. Okay. It's kind of easy. I don't want to repeat. Okay. And lastly, we can see the whole relationship between the gas, liquid that you have. Okay. Alright. So tolong fahamkan sahaja. Okay. Alright. So yang ini boleh cuba. Okay. Ky and Kg. Alright. So in this case, alright, they use Kg. But you can refer to your textbook. What is Kg? Okay. What is Kg? Okay. Because here we have a relationship of K, Kc and Kg. Dia macam tu. Okay. Because this is constant. Okay, constant to see the relationship. The relationship between the gas and the liquid. Okay. So you have different cases, which is flux equation for equimolar counter diffusion. The second one is flux equation for A, diffusing through stagnant and non-diffusing B. Okay, so you have two cases, and then you combine both and see the relationship. Okay, so this is interface mass transfer. So when I talk about interface mass transfer, we talk about the transfer of gas into the liquid. Okay, the transfer of gas into the liquid. So I'm going to give you the video regarding to the interface mass transfer explanation, because this is a very important part that you need to understand to explain the definition of interface mass transfer. Interface mass transfer, we are talking about between the two phases, liquid and the gas, how the transfer occur, how the diffusion occur between the gas and the liquid. And its process only occur at the thin layer between the gas and the liquid, right? Between the gas and the liquid. So the gas will transfer into the liquid. So the solutes that you have must be in the gas. Okay, so you would like to collect the the one that you are interested to be separated. Okay, the component that you are interested to be separated should always call solutes. Yeah, solutes. All right, and your liquid will remain as what we call solvent. Liquid, where the transfer of solutes into the liquid occur, the liquid is called solvent. So I will give you the video regarding to this interface mass transfer. So please watch that video. Okay. So kita tak ada masa. Okay. So ni tak ada apa. Just for your information only. Okay. So the rest is for your information. Okay. Your knowledge only. Okay. So your focus for this subject will be, okay, saya repeat daripada awal. So take note on what you have to know. Okay. First chapter, that definition of mass transfer. Second, definition of diffusion. Okay. That involves single component and binary components. Okay. Next, Fick's law. You need to know how do you use Fick's law in terms of mole fraction and concentration. Next is to use binary mixture. Okay, so when you talk about binary mixture, so you talk about diffusion of only one component. There are two equations that you can use in terms of concentration and in terms of partial pressure to do the calculation. Next is molecular diffusions. So you are talking about more than one components, A and B. But when you discuss one by one. Okay, each component first, one component first, and then followed by another component. And then you have equimolar counter diffusion in gas, where you have this relationship and where you consider your difference in concentration gradient in terms of partial pressure to see how the motion proceed. Okay, before this you mentioned about higher to lower concentration. When you talk about partial pressure, it's from higher partial pressure to lower partial pressure. Okay, next. So saya summariskan ni apa yang you patut tahu. And then you should understand what is diffusion process together with convection. And then you need to understand this one, the below part, how you get the calculation, which is total flux of A, diffusion plus convection. You have two terms that you're going to use. Next, okay, you manipulate the equation, okay, until you get the final equation. So this is the first part is the molar diffusion part. The second part here is the convection parts. Okay. Next, you go for diffusing A, non-diffusing B. Okay. So components that you're talking about. Okay, in a tube. Okay. Then make sure that total flux of B is equal to 0 because B non-diffuse. And then you differentiate the location Z1 and Z2 and the direction of molar flux and total flux. So this is the direction of total flux and A. So that's why you have these arrows. If you were to label the diagram, make sure you label everything. You miss one label, meaning that you're going to lose certain marks. Okay. Now the air in bulk, they move very fast and in a large amount. Okay, so that's why partial pressure at this location between the tube and the environment is given by 0 partial pressure for benzene. Okay, next, summariskan. So diffusing A, non-diffusing B, you have two equations can be used. Equation number 10 and equation number 11. Both can be used. Okay. But for the equation number 1, okay, you have PA and PA only. In equation 11, you have PA and PBM. Okay. So you need to know the total pressure and the partial pressure of A together with PBM. Okay. Next. Ini tak payahlah. Buat diffusion in liquid. So this is apa kita panggil? Introduction sebenarnya. Introduction before you go to the next chapter. Application, you must know at least one example. Okay, at least one example on liquid-liquid extraction, gas absorption, oxygenation of river by air. At least you should know. Okay, this one is only revision and introduction. So this is introduction of liquid-liquid extraction. You have inlet stream. You have the dual inlet stream, which is called solvent stream and feed solution stream. And then you have your product stream, which is called raffinate stream and extract stream. So ada 4 streams when you're dealing with liquid-liquid extraction. Okay, what you are interested in is called solutes. Solutes will be attracted to your solvent. Okay, so you get your extract here, which is the objective of the separation, and you have raffinate, which is the waste part of your, not really waste, but what you don't want. Maybe you would like to process this further, since you have still have a red components here, which is your solutes that you would like to recover. Okay. All right. So this is application of gas absorption, chapter 4. Okay. You have 4 streams. You have solvent stream. You have feed gas stream. You have extract stream kat bawah, and then you have raffinate stream dekat atas. Diffusion only occur at the thin layer, at the surface area between the gas and the liquid. That's all. Okay, so you need to increase the contact area between the liquid and the gas. Okay, so this is equimolar counter diffusion in liquid diffusion. So this is where you're going to use, this equation is when you're going to use for the liquid diffusion. Okay, so you have to know about this one also. We have, you're going to have, you have one example in the textbook. So read the textbook. I don't have time to mention everything here. So this is extra knowledge that you have. Okay, extra knowledge, extra knowledge, extra knowledge, extra knowledge, extra knowledge, extras. Okay, semua ni extra. Sampai ke belakang ni semua extra. Okay, awak nak baca, nak senang faham, go to your textbook. Okay, so that's all for this chapter. Tak ada apa dah. Okay, sorry. And this one is very important. Interface mass transfer. I'll give you the video. Okay, so you can watch the video and understand further.